Hi everyone, welcome to CS188 exam prep number 8. My name is Ryan, and today's topics are going to be about sampling, including rejection sampling, likelihood weighting, and Gibbs sampling, as well as VPI. So I'm just going to dive right into the problems. So in question 1, we're given the following basenet, and we have these two observations. So these are evidence variables, B equals plus D, and D equals plus D. And we're also given the following CPT, where each CPT corresponds to a node in the basenet. And what we're asked to do in part A is to consider doing Gibbs sampling for this example. And essentially, if you recall Gibbs sampling, what we do is the first thing that we do is arbitrarily assign each of our variables in the sample that we're taking. So for example, if I'm considering variables A, B, C, and D, I would arbitrarily assign variables to values such as A equals plus A, B equals minus B, etc. And then I would make sure that all of my variables that are evidence variables are consistent with my evidence. So for example, right here, these two are my evidence variables. So I need to make sure that my sample is consistent with that. So in this case, my sample is plus A, plus B, plus C, and plus D. And we see that this is consistent with our evidence as well, because B equals plus B and D equals plus D. So that's capital B is equal to plus B and capital D is equal to plus D. So now what we do in Gibbs sampling is we basically, for each variable, we unassign the variable and then we resample its value based on the distribution of that variable that we're resampling, given the other variables in our sample. So what does that mean? So for example, if this is our sample and our goal is to unassign the variable C and resample it, what we're essentially trying to compute is going to be the probability of C given the rest of the variables in our sample. So in this case, we have A, B, and D, and they are assigned to values plus A, plus B, and plus C. So that means I'm looking for C given plus A, plus B, and plus D. And we can see that this goes hand in hand with what we're trying to compute here. So now the actual question is, how do we compute this probability? Well, right now we have our basenet and we have a bunch of these CPTs. So what we can do is use Bayes' rule to essentially come up with this distribution accordingly. So for example, let's say I want to figure out probability of plus C given plus A, plus B, and plus D. By Bayes' rule, this is the same as doing probability of plus A, plus B, plus C, plus D divided by the joint distribution of just the right side of the condition. And in this case, just to set it up for later, I'm going to write this as the following. The probability of plus A, plus B, plus C, comma, plus D, plus the probability of plus A, plus B, minus C, plus D. And this comes from the fact that for a joint distribution, if I sum out over the possible values of a variable, it's equivalent to writing the distribution without that variable. So this just comes from the law of total probability, where recall if I do sum of P of A comma B over A, this is equal to P of B. Since I can sum out a variable and sum over the possible values of that variable to get the distribution in terms of the other stuff. Okay, so now how do I calculate these joint distributions? Well, if I'm given all the CPTs in our basenet, we know that the product of all the CPTs is just equal to the joint distribution. So from here, I can kind of like match the CPTs to their appropriate values and then just get the results. So for the top, if I look at the product, I get 0.5 for P of plus A times P of plus B plus B given plus A, which is 0.8, times P of plus C plus B, 0.1, and then P of plus D given plus A comma plus C, which in this case is 0.6. And then I divide this by the same thing, since we see that these two terms right here are the same. So we have just 0.5, 0.8, 0.1, and 0.6. And then we add that with the same sort of setup, except instead we have minus c instead. So what does that entail? We have 0.5 and 0.8. Notice that those two probabilities are not dependent on the value of c. Then we need to do probability of minus c given plus b, which is 0.9, and the probability of plus b given plus a comma minus c. In this case, that is 0.1. And then here I can just kind of like cross out like terms. So 0.5, 0.8, 0.1 from each. And this is just equal to 0.6 over 0.6 plus 0.9 is equal to 6 over 15. And that is going to be equal to 2/5. And so this is the probability of c equals plus c at the next step of given sampling, 2 over 5. Now for the second option, or sorry, for the second probability, so probability of c equals minus c at the next step of given sampling, you could do the same procedure where you calculate all the values using our joint distribution and Bayes rule, or you can just do 1 minus, because notice that the probability sum of these two must add to 1. So we know that P of C equals minus C, given all that stuff, is equal to 1 minus 2 over 5, which is equal to 3 over 5. So the answer here is 3 over 5. And something you'll notice with given sampling is that notice how a lot of these terms canceled out immediately, right? So 0.5, 0.8 right here canceled out. And the reason that it actually cancels out is because the probabilities up here don't contain C in them, right? Because C is, or these probabilities are constant between all of the terms in our probability. So therefore, we can just kind of also say that we can write the probability of this C equals plus C given the rest in terms of only probabilities that contain C. So for example, if we had just ignored A, probability of A and probability of B given A, we could have just gotten the same answer more directly. Here I just wrote it out just to like illustrate what happens when you eventually cancel out the terms. Okay, so let's move on to part B. So in part B, consider the following sampling scheme where we basically do rejection sampling on variables A and B. And then we take the sampled values for A and B and then perform likelihood weighting. And so recall what we do with rejection sampling first. For rejection sampling, we get a sample and then reject it if it's inconsistent with our evidence. Inconsistent with our evidence. So notice right here in part I, we're asked, okay, which of the following samples would be rejected by the rejection sampling portion of our hybrid scheme? So let's recall from our previous part above, our evidence variables were set as B equals plus B and D equals plus D. So that means any sample that is inconsistent with these two things is going to be rejected by rejection sampling. Therefore, we see that this one right here and this one right here would get rejected because they both have minus B instead of plus B. So these two are inconsistent. Okay, now for the next part, we're decoupling away from the previous part. And so now we have a new set of samples and we want to fill in the weights for these samples using our hybrid scheme. So recall with likelihood weighting, the way that we actually determine weights is for each of our evidence variables, we take the probability of that variable given the rest of our other variables in the sample and then multiply by 1 to get our weight. And so the first part to notice about this hybrid scheme is that A and B were set from rejection sampling. So what that means is we don't need to consider them for our weight that we're using for our likelihood sampling part of our scheme. So now the real question is, what do we actually have to consider in that case? Well, we know that our evidence variables are b equals plus b and d equals plus d. And notice this is from rejection sampling, and that means this one is from the likelihood weighting. So now what that means is all I need to do for each of these weights is do 1 times the probability of getting plus d given the remainder of our sample. And in this case, that just comes down to reading the values straight from this table. And so if I read the values straight from this table, for example, we see that in the first sample, for instance, we have plus d plus b, or oops, plus b minus a and minus c, which corresponds to plus d minus c minus a, so right here. And then we would read that value off here, so 0.5, and that's just equal to 0.5. So notice, like normally, if you had multiple evidence variables, you would take the product of all their different weights, of all their different probabilities, and multiply them together to get the weight. But in this case, since we're only considering one evidence variable, technically we're just doing 1 times the probability that we find in our table. So reading off straight from the table, we could just fill in the rest of the rows: 0.1, 0.1, 0.2, and 0.6. And so if you just like take a look at each of these, you just see that that sample is consistent with the values in our table. All right, cool. And now for the last part right here, we're asked to use our weighted sums from part II to calculate an estimate for this query. So probability of plus A given plus B comma plus D. And this is really something to do with sampling, because all sampling is it allows you to take the weighted combination of like samples that are consistent with your query and then divide by the total to get your estimate. So in this case, if we look at our values up here, our weights 0.5, 0.1, 0.1, 0.2, and 0.6, we know that we want to take the samples that are consistent with our query. So in this case, our query is plus A plus B plus D. So we have to take all of our samples which contain plus A, plus B, and plus D. So here we have plus A, plus B, and plus D for these three. So that's a total of 0.1 plus 0.1 plus 0.6. And then we divide this by the sum of all of the samples that we've taken so far. And so in this case, that would be 0.5 plus 0.1 plus 0.1 plus 0.2 plus 0.6. And this overall comes down to 8 over 15. So that would be our estimate of this query. All right. And now the last part of this question asks us to design an alternative hybrid sampling scheme that combines likelihood weighting and rejection sampling as follows. And so for each scheme, we want to decide whether it's valid or whether it's invalid. And valid in this case just means that the weighted sample is going to correctly approximate the distribution that we're looking for, which is probability of A comma C given plus B comma plus D. So for the first one right here, we are collecting a likelihood weighted sample from the variables A and B, and then we switch to rejection sampling for C and D. And in the case that we are rejecting, we throw the whole thing away and then resample starting from node A. And intuitively, if you think about the procedure right here, this would make sense, because every time that you see something that's inconsistent with our current distribution, we need to throw away the whole thing. And we just, this is like the best way to actually merge the two sampling methods together. So in this case, this is actually valid. And you can say that it's necessary that we must throw out the whole sample in its entirety. Because if you don't, for example, you can get different cases where, for example, we no longer affect the values of the previous thing that we've sampled. Or like, for example, when we query the distribution for other variables, and then we only keep half of it, we no longer have the effect of the first thing that we sampled affecting the next thing that we're sampling. And this can be a problem if we're going to consider the the sample as something that's validly approximating the distribution that we're looking for. So in this case, this is valid and good because we throw the whole sample away. And now, like I was just saying, in the second case, the difference right here is that in case of rejection, the values of A and B in the sample weight are retained. So pretty much from what I was saying, you can probably tell that it's invalid. And I guess like good multiple choice test taking tips, probably one is valid, one is invalid. But if you want to think about the reason why, we can consider like for an evidence, D equals plus D, for like some sort of example evidence, we can notice that this would have no effect on the values of A that are sampled or on the sampled weights. If we were to, for example, reject our values of C and D and then resample just those values. So no effect on values of A that are sampled or on these sample weights. And pretty much what this entails is that since we retain values, we end up essentially kind of sampling A from a different distribution that we're looking for, where previously, since we're doing it A, B, and then C, D, we're essentially sampling according to P of A given plus B, when what we really want to be sampling is P of A given plus B comma plus D. But we don't do that if we are like splitting this whole sampling method into these two distinct steps. And intuitively, you can also think of another reason why this is incorrect, such that if, for example, the probability of, let's say, plus D given plus B was 0, for example, and then we always get probability of minus D given plus D, or something like that, where we, based on the initial values that we have, what ends up happening is that there are no actual possible values that our sample can take that will be consistent with our evidence. And then we would keep just resampling over and over again to like no end. And then in that case, this sort of method would never even generate a valid sample. And so you can think of it as invalid in that sense as well. All right, well, that concludes problem 1.